Oopsie daisy, here we go. So, welcome to another Astronomy on Tap. I'm hoping we can see everyone. Yes, there we go. So, welcome to Astronomy on Tap, the March edition, which is again online. Let's see if I can use. Irene or Maren, do you want to just make a bit of noise so I can just check that I can hear you?
Yes.
Hello.
Okay, that's good. Yes, here we go. I'll start again. Welcome to the March edition of Astronomy on Tap, which is the third one online because of the ongoing corona restrictions. So we hope that everyone is safe and at home, and we will see you live soon. So tonight's theme is women in astronomy because, well, yesterday was International Women's Day, and I hope that you had a nice day. It's a day where we kind of celebrate the achievements of women and also think about the steps that we need to take to make more progress. So for this month, we have decided to collaborate with Kvinder i Fysik, so the Danish Women in Physics Society. Maren here is the chairwoman of that. She'll tell us a little bit about KiF and some upcoming events during the break. KiF have done a lot of work raising the profile of women in physics, just building awareness. And one thing they do is give out a KiF Prize every year. So last year's KiF Prize winner is Irene Tamborra here. So Irene has studied in Italy and then worked in Germany and Amsterdam and has made her way to Denmark, where we're very lucky to have her speak with us. And she has started to establish her own research group which looks at neutrinos, or as she calls them, ghostly messengers, to understand some of the most energetic explosions in the universe. So she has won many prizes, and including last year's KiF Prize for being an inspirational role model. So we'll let you take that away.
Thank you. So let me share my screen first. You see my presentation now, right? Okay. So hi, everyone, and thanks a lot for the invitation. I'm very happy to be here. So when the Apollo astronauts went on their first moonwalks, on their way back, they had the dust on their suits, and they started to smell it and to taste it in the attempt of learning and getting to know this unknown land. So this is, I think, a very clear example of how humankind has been relying on our five senses to getting to know the unknown. Now, when we move forward towards something that we cannot reach physically, then the only sense that is left to us is our sight. And indeed, we have used our sight since centuries to learn about the cosmos. And gradually, we have also expanded to different wavelengths to study the unknown in the universe. Today, we have a new messenger that can help us to learn about the universe, and this is the neutrino. But what are neutrinos? So if you think of any living creature or our planet or any object that is surrounding us, then we can break these objects in some fundamental constituents that are protons, neutrons, and electrons. And then these particles will be bundled together to form atoms. However, for every proton, neutron, and electron, there are billions of neutrinos. The word neutrino means a little neutron, which is then, as the word is telling us, a neutral particle. And this is also an elementary particle, which means that we cannot break it down in further particles. The size of the neutrino is 1,000 times smaller than the size of an atom. And these particles are the second most abundant particles in our universe after photons. So being so abundant, I can already tell you that in order to understand the universe, we need to understand neutrinos. neutrinos are produced in a very wide variety of sources, like, for example, in nuclear reactors, in particle accelerators, like at CERN, in the atmosphere, in the Earth, and also in a wide range of astrophysical sources, which, like the sun or supernovae, or any kind of sources, like, and also in the Big Bang, so at the very origin of our universe. Now, are neutrinos important to us? The answer is yes. Indeed, without neutrinos, our sun wouldn't shine, supernovae would not explode, and all the elements that are crucial to our life wouldn't be here. So without neutrinos, we probably wouldn't be here. The sun is a star that is relatively young and is powered by fusion of hydrogen. And while these reactions are happening in the sun, then neutrinos are produced. And then they stream freely until they reach Earth, and they can actually reach us. Indeed, while I'm talking to you, billions and billions of neutrinos are zipping through you every second. Now, the very funny thing is that neutrinos can actually zip through you even at night. Indeed, these particles have a very, very weakly interacting nature, which means that they are produced and then they almost don't interact at all. Then they can cross the Earth without interacting, and then they can reach us. And maybe now you are wondering, if we are continuously showered by all these neutrinos, then are neutrinos dangerous to us? Well, on average, we expect that only one neutrino will interact within our body in a lifetime, and it will produce only one electron. So we shouldn't worry, neutrinos are safe. However, since they are produced in the sources and then they reach Earth without basically not interacting, they are carrying a lot of information about what is happening in the core of the source. So we are very interested in hunting them and learning about the secrets that they carry about the sources. In order to do that, we use some neutrino telescopes, which are the analogous of telescopes that we use for photons, but they are for neutrinos. And here you see a map of all the neutrino detectors or telescopes which are currently working. And the ones in parentheses are upcoming detectors. Now, given that these particles do not interact very much, in order to detect neutrinos at Earth, we need to build huge detectors. So an example is the Super Kamiokande detector, which is a detector built in the Kamioka mine in Japan. And one of the features also of neutrino detectors is that we need to build them underground in order to have a safe environment that is not contaminated by background. And in the case of Super Kamiokande, this is nothing else than a huge tank of water. And you can see here, there are two scientists on a boat on the top level of water. And these buttons that you see here are electronic eyes. So these are called the photomultipliers. And they are nothing else than some sensors that when neutrinos interact with protons in the water molecules, then a positron is released, and this will hit on this button and will basically release a flash of light. So this is how we detect these neutral particles. And here you can see the shape of the detector. This is the water tank, and here this is the top of this experiment. A similar principle is also the one on which the IceCube Neutrino Observatory is also based. And this is an observatory that is located at the South Pole in Antarctica. And here you see the base station where the data are analyzed. And then a bit far away from here, underground, there is the detector. Now, in order to give you an idea about the size of this detector, here you can see the Torifel that is plotted just for comparison. So in this case, we have a lot of strings that have been deployed in eyes. And on each of these strings, there are a lot of electronic eyes that are the analogous of the ones that we saw for Super Kamiokande. And here you can see a zoom in on one of these eyes. And again, this is the way through which neutrinos are detected. Now we are used to look at the sun by naked eyes. However, the image that you see here of the sun is instead an image of the sun that has been taken through neutrinos. And actually, the detection of neutrinos from the sun has been extremely important because the production of neutrinos in the sun is very sensitive to the temperature of the sun in the region where neutrinos are produced. So by detecting neutrinos in the sun, we have from the sun, we have then learned about the way the sun is working, and we have tested our theories. Now, the next frontier is to learn about core collapse supernovae by using neutrinos. In the case of core collapse supernovae, those are nothing else than the final stages of the death of stars that are at least 8 times heavier than our sun. And when we think of this kind of stars, we start from something like our sun, where hydrogen is burning, and then as soon as hydrogen stops burning, we produce an helium core, which in itself will start burning, and we start producing heavier and heavier elements like carbon, oxygen, and so on, until we reach the final stages of the life of these massive stars, where the core is made of iron. When we reach the iron core, then the binding energy of iron is the largest one, and then the star cannot be anymore in equilibrium because we cannot produce any more heating by fusing those elements, and therefore the star collapses onto itself because of its gravitational forces. And then a shockwave forms in the core of the star, and neutrinos contribute to power this shockwave to finally trigger the supernova explosion. So one thing that is very interesting is that in the course of these burning stages, we take 1 million years, and the time that we take once we reach the final stages of the burning, then become very, very short, until a few seconds in which the whole collapse actually happens. Now, when a supernova explodes, we see it as an extremely luminous transient in the sky. And here you can see some images of where before the supernova was occurring. And then here you see these bright spots in which the supernova happened. The supernova is so luminous that is outshining its own galaxy for the time, for a certain amount of time. And we limit so much energy that is even larger than the one emitted from the sun throughout its own entire life. However, the energy that is emitted in a supernova through photons, so through light, is actually only less than 1% than the whole energy of this object. The 99% of the energy of a supernova, of the gravitational binding energy of a supernova, goes instead into neutrinos. And we produce 10 to the 58 neutrinos during the collapse. This means 10 with the 58 zeros after that. So this is such a huge number of neutrinos that is already telling us as this collapse of a massive star is completely driven by neutrinos. Now, before I told you that if we consider the neutrinos that are emitted from the sun, then we should not be worried because we don't get so many neutrinos that they can be dangerous to us. However, if the sun were a supernova, which is never going to happen because the sun is too light to become a supernova, then even aliens on Mars would be incinerated by neutrino radiation because there will be emitted so many neutrinos that then they can become dangerous to us. The first supernova that we have detected in neutrinos is the supernova 1987A. And the reason being that we expect one supernova to explode every second in our universe, but then in order to detect these supernova neutrinos, we need that the supernova happen in our galaxy or in close by galaxies. And so we expect more or less 2 or 3 of these supernova per century. Now, in 1987, when we detected this supernova, not many of the detectors that we have today were at work, and some of them were also off. So we only detected about 20 neutrino events. Although these were few events with respect to what we can detect today, that would be about like 1 million of neutrino events for one of the existing detectors. Then these were crucial to probe the stellar collapse. Now, the conditions that that occur during the explosion of massive stars are so extreme that we cannot reproduce the collapse in a lab. And so what we do instead is to simulate what happens in the core collapse by relying on supernova simulations, on computer simulations. Those are extremely sophisticated simulations, which that employ tens of thousands of CPUs and take months of computational time to simulate what happens in fractions of a second just before the collapse occurs. What you see here is one of these simulations in 3 dimensions. And what is interesting is that we start from something that is very spherically symmetric. And then there are those sloshing motions that start to develop that are nothing else than those motions of matter as the shock wave is acquiring energy from neutrinos. And all this matter is just boiling. And here you can see that at the center, there is the neutron star that is starting to form and that will be left soon after the explosion. Now here the simulation stops, but then soon after we just have the explosion of this massive star. So what happens is that the neutrinos are the only particles together with the gravitational waves that are produced really in the core of these stars. And note that in this simulation, we are just looking at 1/4 of 1 second. So it's really a very short amount of time. However, we will be able to detect neutrinos from this kind of supernova. And here you see what we will see in a detector, like, for example, the IceCube Neutrino Observatory. And you can see that these modulations that we will see in the neutrino signal are nothing else than these motions of the shock wave that you have seen before, these motions of matter, as it is acquiring energy just before the explosion. Therefore, by detecting these particles, we can study what is happening just before the star explodes. And we cannot study this otherwise. Now, another thing is that I mentioned before that neutrinos are interacting very weakly. And this means that they can reach Earth a few hours up to 1 day earlier than photons. And for these reasons, we can use neutrinos to alert astronomers that there is a supernova happening so that then they can point their telescope in the right direction. And to this purpose, there is a network of neutrino detectors that is called SNEWS that is releasing an alert as soon as a supernova goes off. And if you want, you can go on this website and you can sign up to get a text message as soon as supernova explodes. Moreover, we can use also neutrinos to determine the direction in which this supernova is exploding. And this is important because some supernovae occur in regions that are very dusty, and so we cannot detect them in photons. Moreover, we also know that probably half of all supernovae that we see are actually forming black holes instead of neutron stars. And if a black hole forms, then we cannot emit electromagnetic radiation, and only neutrinos and gravitational waves will tell us that there is this collapse happening in the sky. Moreover, when we synthesize, when we fuse and we produce all these elements during the stellar collapse, and as I mentioned before, as we move towards heavier and heavier elements, the burning stages take less and less time. Then, as the supernova explodes and the shockwave propagates in the outer space, we basically release in the outer space all the elemental debris of all the elements that we have produced. And they start swirling down together with the gas and stars that then probably will also form new stars and new planets. One of the hottest and most burning questions at the moment is to understand where elements that are heavier than iron actually form. And by this, I mean, for example, gold or platinum and so on. And it's possible that given the high densities that we have in the core of collapsing stars, then protons and electrons smash together to form neutrons. And then we can have many neutrons together because they are neutral and they don't repel each other. And iron nuclei can eat a lot of neutrons. And through this process, then we can get to produce the heaviest elements that we have. In all these reactions, we always need the neutrinos. So without neutrinos, we couldn't produce these elements. So I want to leave you with we have just taken this cosmic trip to the core of stars, or massive stars. And I want to leave you with this quote by Carl Sagan that says that the nitrogen in our DNA, the calcium in our teeth, the iron in our blood, and the carbon in our apple pie were made into the interior of collapsing stars. We are made of star stuff. Well, I hope I convinced you that we are made of star stuff because of neutrinos. Thank you.
Thank you, Irene. So if anyone has any questions about neutrinos, these ghostly particles, please put them onto the chat and I'll be keeping an eye out. But while we wait for questions to come through, I have a few questions myself. Where do I want to start? Okay, one of them was you're going through the detectors, like the Super Kamiokande one and the Ice Cube one. They're always these giant things with water and ice. Like, do they have to be that big, or do you have to use water? Can you use something else? Or yeah, why are the detectors always so massive?
So you can use something else. So I showed you like the example of water, but you can also, for example, use argon, or you can use some special mixtures of other materials, and they are all fine. But we do need them to be very big because neutrinos don't interact a lot. So in order to increase the possibility that they will actually interact in the detector, then we need to have something that is very large. And so, for example, right now, for the next generation of the detectors, we are going towards kilometer cube objects.
Okay, wow.
So they are quite big.
What else do I have? We're still waiting on questions to come through. How close does super... Yes, so you said the neutrinos from our sun are mostly harmless. Well, they are harmless. But you did also say that supernovas would produce enough neutrinos to be harmful. So how close does a supernova have to be before we would, I guess, be burnt by neutrinos or something? So I don't remember on the top of my head the exact distance, but it's below 1 kiloparsec. I think it's about like 0.2 or 0.3 kiloparsecs, and then it starts to become dangerous. There is a computation that has been made, and there are also some comics about this. Yes, so we should be careful. 3 parsecs. So, hold on. How close is our closest star system? I'm just trying to think about this in terms that other people would understand. So what is 3 parsecs in light years about?
Yeah, I don't know, because I always think in parsecs.
Yeah, that's okay.
Help you.
I think so. Alpha Centauri is a bit more than a parsec away. Okay, sorry, people, but we'll get back to you on that. We do have a question though. Okay, so one question says, you said neutrinos are faster than photons in the way from when they come from supernovas to us. How can you calculate the speed of a photon? Which, so does it depend on the dust in the way and other factors? So I guess the question is, why are the neutrinos faster than the photons?
Yeah, so both neutrinos and photons are moving at the speed of light, because I didn't mention this, but neutrinos actually have a mass, so their velocity is a bit smaller than the speed of light, but is still very, very close to the speed of light. However, photons interact way more often than neutrinos, and this is how they are slowed down. And sometimes they even don't reach Earth. While neutrinos, they just never interact. So they leave the source and then they keep just streaming. This is why they can reach us earlier.
There you go. Yes, so one question from Awesome Quantum was, how massive are neutrinos? Do you think they're relatively massive?
So we don't know yet which is the absolute mass of neutrinos. We hope to, this is one of the still mysterious things which we hope to discover and to measure soon. But right now, the most stringent bounds are coming from cosmological data, and they tell us that the mass is around milli-electron volt. So it's very, very, very light. It's it's like much smaller than the mass of a proton of an electron, like 10 orders of magnitude smaller.
Yeah, wow, that is tiny. Someone clarify for us, 1 parsec is a little more than 3 light years. So
okay, awesome.
Supernova has to be within 3 light years, so it's, I guess, 3 parsecs and about 10-ish light years away. I don't think we know any big stars that close.
No, I think we are safe for now.
Yeah. Please send more questions our way. I do have some more. So, I remember this. So there was a controversy a few years ago, probably about a decade ago, about neutrinos being measured to travel faster than the speed of light. What happened with that? Because I guess that's probably why some people were confused here, why we're seeing the neutrinos before the photons. Is it because they're traveling faster than the photons? But I guess... so
this couldn't happen, and indeed, like, there was a problem. I think it was a screw in the detector that was not in place, and this is why then there was this whole a confusion and story about neutrinos traveling faster than light. So this didn't happen.
Yeah. That's pretty wild that a screw could throw things off so much. We have some more questions. So Louise Hopner asks, how do you actually detect the neutrinos inside the detector? You might have said it while you were discussing it, but it always was a bit hard to understand. So what is happening inside a detector?
So it depends on which detectors we consider. For example, in the ones that we have seen, that I showed you, what happens is that the neutrinos interact with the protons in the water molecules, and then this produces a neutron and a positron, and then the positron will generate a Cherenkov radiation that is detected by this electronic eyes that I showed you. In the case, for example, in which the detector is made of argon, then the neutrino interacts with the argon atom, and then this will produce again like a charged particle that can be detected. So the fact that the neutrinos are neutral means that we can only see them through these kind of reactions that then produce charged particles.
Yeah. So you said they interact with the protons, but the neutrinos are neutral. Is it just like a chance hitting of the neutron and the proton, or is there some other interaction that's happening?
Yeah, it's like a beta reaction. So you just can conserve like all, you conserve charge, you conserve everything.
Okay.
Because then you produce a lepton, so also lepton number is conserved. Just don't go too technical.
Yeah, I was like, I did lepton numbers and stuff many years ago, so I don't remember anything. But we do have more questions. Okay, do you know, so from Jürgen Skut, I hope I pronounced your name correctly. How do you know how to synchronize the clocks in all the detectors? There must be a lower limit for how precise the synchronization can be.
You mean to release an alert?
I don't know if it means for releasing an alert or, well, yes, I'm not quite sure, but let's say that is what they were asking. So what would your response be?
Yes, so we basically can compute. So there is an uncertainty with respect to which is exactly the first neutrino that hits the detector with respect to the rising time of the signal that we want to see. But we can compute more or less which is according to the location of these detectors when the neutrino signal is expected to arrive. And of course, there is an uncertainty, but this uncertainty is below the 1 second in terms of, is way below 1 second in terms of timing. And then all these detectors are synchronized with the one clock that is in one lab. And so they all basically maintain the same time, and we can compute just which is the time according to the location of the detectors at which the neutrinos should reach them. So this is it's a whole mechanism that is basically in place and is working. But it's a good question. Yeah.
That sounds like a lot of coordination to make sure these clocks are exactly on the same time. I guess as they were saying, there's probably some lower limit for how precise you can set these clocks.
Yeah, but it doesn't like whatever is the lower limit, actually it doesn't affect the signal, because still we are talking about a few hours up to 1 day afterwards from when we detect photons. So this uncertainty is below 1 second. So it's very, very small with respect to the time after which photons arrive.
So how many supernovas have we caught because we could see the neutrinos coming from them first?
So now we have seen the supernova 1987A, and then we are waiting for the next one coming, because now we have many more detectors that are working. And at the same time, also, I didn't mention this in the talk, but we can also detect all the neutrinos coming from all supernovae in the universe just as a stationary signal that is always there. So they just keep coming. And this is something now people are studying to make it happen, and it should happen within the next few years.
So this leads nicely into another question we have. Daniel Melisani says, slightly off topic, but how about extragalactic neutrinos? Is their source clear or still open? I remember a case where an association with an active galactic nucleus was reported.
Yeah, so we still don't know from where they're coming from. We have observed some of these neutrinos that were in coincidence with an active galactic nucleus, indeed, but it's very difficult to explain how we could match what we see in neutrinos and what we see in photons. There is also another association of one neutrino with the tidal disruption events, so when a star is swallowed by a black hole. But also in this case, we are still working out which is the exact way to make work all the data that we have, because it's still a mystery. So in the end, we still don't know from where these extragalactic neutrinos are coming from.
Just for reference, if you didn't know what an active galactic nucleus is, it's just it's a black hole at the center of a galaxy that's eating something at the moment that we see it. We do have another question. So Louise Hupner says, how many neutrinos interact in a detector in like a day? So I guess, what is the day-to-day of a detector?
So this depends on the source. For example, we see a few solar neutrinos per day. In the case in which we have a supernova, then in one day we will have 1 million of neutrino detectors, of neutrino events. But then if the supernova happens in our galaxy, and then in addition to this, we also needed to consider, for example, neutrinos from the atmosphere that continuously come. Or if the detector is close to a nuclear reactor, then there are also these other neutrinos that are continuously coming. And those are all sources like of steady noise with respect to when, for example, we want to detect a supernova. So usually neutrino detectors are very busy, both at day and night in detecting neutrinos.
And you just gotta, I guess if you detect a neutrino, you have to figure out where it came from.
Exactly. Yeah.
We have another question, which is, I was thinking about this as well. So last month's event was about, was celebrating 5 years of gravitational waves. And I learned that there was one event where we didn't detect neutrinos. So this question from Jürgen says, it could be interesting to hear whether it has been possible to link a neutrino event to a LIGO event. Has that happened yet, or has it not? And has that been a mystery?
Yeah, so I didn't talk about this because of time, but of course, for example, in the case of supernovae, we can also see gravitational waves. And then we could, and as I mentioned in the talk, both neutrinos and gravitational waves are the only ones that are produced in the core of this supernova. So really, they give us the chance to learn about what is happening in the core of these sources. And then the other case that it's very likely is when two neutron stars merge, and then like we see gravitational waves, and this is what we saw in 2017. And their neutrinos are also produced. So in the case of the event that happened in 2017, many neutrino detectors looked for neutrinos. And we didn't see anything because those events were too far and were like slightly oriented towards, not towards us. However, if there are more events, and especially if those events are pointing to us, then we will detect together neutrinos and gravitational waves. And this would be extremely exciting.
I have another question about the neutrino detectors. I guess, how well can you figure out the direction of the neutrinos? What does that depend on?
So it depends on, well, it depends on the direction from which they come. But then in some detectors, like for example in Super Kamiokande, instead of considering the neutrinos hitting a proton, we can also consider neutrinos hitting electrons. This doesn't produce as many events as the ones that we have just seen, but it's a way from which we can also reconstruct the direction from which the neutrinos is coming. And then, for example, this would allow to locate a supernova with a precision that is below 1 degree, so in the sky. And so this is comparable to what we do with photons. But we have less events in the detector that go through these reactions. And for example, even the image that I showed you before of the sun, this was taken through this kind of reactions, because you can see that we have reconstructed like the core of the sun and then the outer parts, more or less. And this comes exactly from the direction through which the neutrinos are traveling.
Oh, wow, that's pretty amazing. Okay, I think we might wrap up the question time there, but we'll thank Irene again. Thank you so much for teaching us about neutrinos.
Thanks.
So before we go on to the break, we will have Man, who will tell us a little bit about KiF and I guess upcoming KiF events. So Man, would you like to share your screen?
Yes, thank you, Reggie, and thank you, Irene. That was so fascinating, really, really interesting.
Thanks.
So yes, as Reggie said, my name is Maren. I'm the chairwoman of KiF, or Kvinder in Fysik, which means women in physics. And I will just spend a couple of minutes sharing with you some of the things that we do. And so I need to share my screen, right?
Yeah.
Oh, God. Okay. Yes. Good. All right. Great. So, as I mentioned, Kvinder i Fysik means women in physics, and we were founded in '92 at the Niels Bohr Institute, actually, at a time where there were very few women in the physical sciences, and those numbers have fortunately been improving since, especially since more young women choose to study physics nowadays. But the numbers are improving slowly, and most importantly, women are still underrepresented, especially at the higher levels, the higher academic levels. As you move up through the levels of PhD students, postdocs, associate professors, and especially as you get to the professorship positions and head of institute and such positions, there are very few women represented in Denmark and worldwide, really. So some of the things that we do is that we try to promote the visibility of the women in physics, those women that actually are working in the physical sciences and do excellent research, and such as we've just seen by Irene, because these women are really role models. So what we're trying to do is break some of the stereotypes of who does physics and what does a physicist look like. We conduct interviews with various successful female physicists who talk about their careers, their choices, and the research that they do. You can read some of these on our website, and I will share that link in a few minutes. We do something called a takeover on Instagram, where again, women from at different levels of their career show their life and their studies or their work through pictures and texts. Then we award annually the KiF Prize, which is given out every year at our annual meeting. And Irene was last year's winner. She received the prize for being really an excellent role model in physics and doing excellent research. We do networking. We conduct online networking events and in person when possible. We arrange different science talks, and we do outreach. And I will share with you one of the next events that is coming up. But I also just want to mention to you that on our library, on our website, we do have a library of articles of interest that really show the statistics, the numbers of the actual facts of what is the situation, not just in Denmark, but worldwide. How is the representation of women in the physical sciences? So this is what I've been looking forward to show you, that we, together with Cinematica, have put together a film series of women in science and some of the obstacles that they faced. So this is coming up this summer. We do not have an exact date yet because we've been holding off until we know when the COVID restrictions will be lifted. But these 4 films we have secured, or Cinematica has secured the rights to show these films. And I'll just show it slowly. I'll just briefly mention that the first film, Bombshell, is actually the Hedy Lamarr story, and many of you may know Hedy Lamarr as a famous movie star, and she was probably really one of the most recognizable of the classical movie stars. But what very few people know is that she actually was an inventor. She had a keen interest in technology from a very young age, and her invention is the basis of Bluetooth and Wi-Fi technology, but she never received the credit for it. And the film actually documents that. So the next movie is Radioactive, which is the life story of Marie Curie, probably one of the most famous female physicists. Picture a Scientist is a documentary. It's a new documentary And it tells the stories of real-life female scientists, not just physicists, and they talk about the obstacles, the biases, and frankly, the outright harassment that they've been subjected to throughout their career at each step. So we will be this will be the first chance you will get to actually see this movie in Denmark. The last movie you may know, it's an oldie but goodie with Jodie Foster, where she portrays Eleanor Arroway, a female astrophysicist looking for life, extraterrestrial or intelligent life. Okay, so these 4 movies will be coming to Cinematica. So so follow Cinematica and follow Kvinder i Fysik to see when the dates will be announced. And so I will leave you with this, which is where to find us on our website, on Facebook, on our Instagram under Kvinder i Fysik, or you can use the hashtag KiF Takeover, and we are also on LinkedIn. So thank you for your attention.
It's okay. Thank you, Maren, for educating us about the work that Kvinder i Fysik does. So I guess Astronomy on Tap will try to share some of this information on our social media as well. Now, I guess, Maren, would you care to stop sharing screen?
There we go.
Yes. So I think now we'll pass on to Nikki, who will open the quiz and tell everyone a bit about the quiz.
Yes, hello. So the quiz is back, and this time there will be questions about neutrinos and also more general questions about women in astronomy. And again, the winner of the quiz will be awarded some tickets for the next real-life event of Astronomy on Tap. Okay, so last time we had some issues with the live quiz because of the lag with YouTube. So now we decided to do it like before, where we have a quiz on Google Forms. So you can just all make it by yourself. You have until 8 o'clock when the second talk is starting, and then we'll close the quiz. So make sure to submit your answers in time. And after the second talk, we'll be going over the answers of the quiz and announcing the winner. So Reggie, I'm not sure, will there be a banner for the quiz, or should we put it in the chat?
I just put the link in the chat, but I'll also have the little slide up with the quiz link. So is it open now? The quiz is open now, is it?
Oh, I'll open it when I'm done talking. So
okay, yeah, I think so. I posted the link in the live chat, and I'll have the slides up, and we'll just have a break and resume a bit before 8. So get on the quiz, I guess.
Okay, I'll open it now. Good luck.
So, welcome back to our second part of the night. So I'll put this into gallery. So, hope that you had some fun with the quiz. And you might have noticed that there was a tiebreaker question. We had to be creative about that. But Nikki is going to go through the quiz responses, and after the second quiz, she'll go through the answers and announce a winner. So while we wait, before you can do that, we'll go on to the second talk of the night. So for many people, it's going to speak of you. No, I guess. Just trying to think of the best way to show this. For many people, Anya Anderson does not need any introduction, but I will still give one anyway because she is wonderful. So Anya has had an extensive career researching cosmic dust, and she is a cross-disciplinarian who has worked together astronomy and chemistry and biology and geology. And also while doing that, she has done so much public outreach and has even written a few popular science books. She has one that's going to be, it's already been released in a couple of languages and will be coming out in English this year about Marie Curie. So that will be exciting. And I guess most importantly for this event, or our Women in Astronomy event, Anya was once a chairwoman of Kvinder e-Physics and has worked so hard to battle some of the difficulties that women in science has typically, historically felt, to pave the way for future women scientists. So Anya will take it away and talk about some cool research that she's been doing.
We're not on. Okay, well, why don't you just introduce it, do it again? That's fine, thank you. So thank you, Raja and Nikki, for arranging Astronomy and TAP, and thank you, Irene, for a very nice talk on neutrinos, and thank you, Maren, for the very nice introduction on women in physics, which is very dear to me. I used to be a chairwoman of Women in Physics for many years, back in the 90s, and it's nice to see the network is still strongly alive, and at the same time, I do look forward to the day when we don't need a network like that. But where I find it very useful is it can be useful to have a safe space where you can share your experiences, because sometimes you bump into situations where you don't know whether it's because you are an annoying personality that you experience this, or whether it's just has nothing to do with you, and it's just a structural thing that's wrong and need to be fixed. So it's one of the things that I made my sort of call, that every time I bump into something that I think need to be fixed, I'm going to keep kicking at it until I get someone to try to fix it. And as we all know, that can be very difficult at a university, because a university is an old and cultural bearing entity, meaning it has a huge amount of inertia, right? And I think one of the gender researchers at University of Copenhagen, she explained to me why it was like that. She said, Anya, you have to remember, University of Copenhagen was founded more than 500 years ago as a university which main purpose was to educate young men to become priests. And sometimes the system behaves like that is still our main mission in life, and that's why, since you are not a man and you don't want to become a priest, that you experience trouble. So I think of that every time I run into something. So, and also thank you for mentioning the graphic novel on Marie Curie. I'm very proud of that particular book, because what we wanted to show was that Marie Curie was not only an amazing scientist, she was also a normal person who ran into normal person problems. So for instance, after her high school degree, she got a nervous breakdown and had to take a year off and be sent to the countryside to some family. And she had another nervous breakdown when her husband died, and she recovered. And I think that's an important story to share, because most people actually run into life and recover. So it's important that we tell young people that, you know, life is a challenge sometimes, but that's also what makes you somehow experience life. And if you get out on the other side, it can actually make you a better person. So, and the movies that Maren shared, I can strongly recommend A Picture of a Scientist. It's almost a bit scary, I would say, because these women have really experienced some horrendous things. But I think it's very good that we talk about harassment and sexual harassment, so that we are all aware that it happens and that we can all take action against it. So I can strongly recommend that. Contact is one of my favorite movies. So I'll definitely go see them, and I hope to see a lot of you out there. But what I've decided to talk about for Astronomy on Tap about the research is actually a paper I have coming out at exactly 8 o'clock. So the embargo is lifted now because it's 8:03. So that's very good. So I'm allowed to talk about it. And I call the title Serendipity in Research, because it's a research result which is a bit funny and actually just came a bit out of the blue, and not something that I was pursuing, but we've had a lot of fun and a lot of challenging times doing it. So now I would like to share with you. So this is the paper, and it's about the zodiacal lights, which most astronomers find not exciting at all, because I'm an expert on dust, and for most astronomers, dust is just something which is super annoying, because it's in your line of sight and it's blocking your sight line when you want to look at galaxies or stars. So dust is just something that's annoying, that's in your way for your observation. But dust is also what actually is the foundation of planets, and it's on the surface of dust that we form molecules. So dust is somehow also the source of life. So it does have a right to be in the universe, I think. So, but this paper actually has to do with the Juno mission. So if you look at all the co-authors I have, then they are all connected to the Juno mission and working on the Juno mission. So the Juno mission is the satellite that you see to the left. And it was actually built to fly out to Jupiter and study the upper cloud layers of Jupiter to understand the atmosphere of Jupiter to a higher extent. It was also a technology testing mission, because normally when you send spacecraft out to the outer solar system, you have a nuclear reactor because there's not very much sunlight, so you need energy to drive your instruments. But they were testing, would it be able to actually generate enough power at the distance of Jupiter by using solar panels? So you see that the Juno has really, really huge solar panels, which is important for this story. So Juno was generated by sunlight for going out to the outer solar system, and on its way. So besides the solar panels, there is another important feature on Juno, and that is that it has what is called star trackers, which is basically just 4 small cameras, because one of the challenges you have when you send out a space mission is actually to know where you are. And the reason that you need to know exactly where you are is that you need to know in which direction the Earth is, so that you can send your signal to Earth and you can keep in contact with Earth. And in order to know where Earth is, you need to know where you are. And a spacecraft like that is not just flying straight forward, it's actually spinning around its own axis to have more stability. So in order to navigate and to be aware of where you are, it has 3 cameras looking in different directions, taking into account this stellar constellations, and comparing to star maps on board in the computer of the spacecraft, so that it always knows how it's turning and what its direction is compared to Earth. As things break in space, then missions like this are always sent up with 4 star trackers, meaning 4 little cameras, so that if one of them breaks, there will always be 3, because you need 3 in order to do proper navigation. If you can't triangulate between 3 different pictures, you don't know where you are. These star trackers are built out at the Danish Technical University by John Leif Jørgensen and his team. And John Leif Jørgensen and I have earlier, like 10 years ago, we suggested to ESA that they should consider building a mission that we called Bering, after Danish explorer Bering, who discovered the Bering Strait. And what we wanted to do with the Bering mission was to have it fly out to the asteroid belt, because we were very curious what was the size distribution of asteroids. Because when people are trying to determine, are Earth threatening by asteroids, then it actually depends on how many asteroids you have in the asteroid belt, and the size distribution is very important. And since it's very difficult to observe the small ones from Earth because they don't reflect very much sunlight, then our idea was that you would just fly a very simple mission with star trackers out there in the asteroid belt, and then you would observe asteroids, and then you would have an idea what the size distribution was. ESA didn't find that super exciting, so our Bering mission was never selected. But John Leif, he was quite intrigued by that idea. So he actually managed, his star trackers were flying on this NASA mission, and he managed to convince NASA that they should have the spare star tracker online at the same time as the tracking star trackers, the 3 stars. So all 4 of them should be operating, and the 4th one could just be looking randomly in space to see if it saw any flying rocks around that we could determine as asteroids, so we could maybe get some sort of handle on the asteroid size distribution that way. NASA wasn't very happy about this, because NASA doesn't really like to have instruments working while it's in transport mode. So they prefer to have as little going on while they're transporting, and then when they get to the object, which in this case is Jupiter, then they would turn on the instruments, and that's sort of a safer procedure. But John Leif can be relatively persuasive when he decides to, so he actually managed to convince them that they should have this star tracker on. So for the first long flight of Juno, it saw absolutely nothing, and nothing happened with that star tracker. And then suddenly the star tracker kept reporting in several times per day that it had seen all kind of bits of lights. And John Leif and his teams, they were very confused, because the lights and the origin of the light didn't fit with asteroids, and they couldn't figure out exactly what it was they were seeing. But eventually what they realized was that what they were seeing was actually that they saw larger dust grains that was hitting the solar panels and actually destroying the solar panels. So it was little chips off solar panels flying by the star tracker that they saw. This they were, of course, not very happy about, because you build solar panels so you can generate power. So you don't want, you know, a lot of gravel hitting your solar panels and destroying them as you're on your way to Jupiter, where you really need the power. But once they got over that, they thought, okay, this sounds interesting. So they called me and said, we have a problem in Houston, but we think you might be interested in the problem, because we actually, by accident and serendipity, have actually made a butterfly net where we are, with the big solar panels, picking up huge dust grains as we are flying through the solar system plane. So what they realized that they were actually seeing is what is normally called the zodiacal light. So the zodiacal light, astronomers have known of for a long time, because it's one of these Anusen things when you go observe. So right before sunset or right after sunset, you have this dust layer in the plane of the solar system that reflects the light from the upcoming or downgoing sun. And that can give you sort of a fake kind of sunset or sunrise, which of course destroys your observations, because you want it to be dark so that you can see the sky. So it's relatively annoying. And people have speculated, where does this dust come from, which is in the solar system plane? If there's any of you who are not astronomers and might think, what is she talking about with the solar system plane? Here's a drawing trying to explain that. So what you see here is not to scale, but you see the sun in the middle, then you see Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. And the solar system is constructed such that all the planets are with the sun and actually in a plane. And the zodiacal light, so the dust that we see, is also in this plane. So people have been wondering, the dust that you have in this plane, where does it come from? Because the only thing which is certain is that the dust that you have will slowly spiral towards the sun. So eventually things move towards the sun. So the fact that we, 4.5 billion years after the formation of the solar system, still have a tiny dust layer that can annoy our observations, indicate that you have a dust source somewhere. You have a supply of dust from somewhere. And that somewhere, most people have assumed, is the asteroid belt, which is this little gravel that you see between Mars and Jupiter of larger rocks that just never really collected into a planet. The biggest asteroid is Ceres. It's about 1,000 kilometers in diameter. And the smallest one, yes, we still don't know that, because Bering didn't fly, but at least we know that there are some which are just a few kilometers inside, and whether they are smaller ones or the smaller ones have all disappeared, that's still an open question. So Juno, as it was flying on its way to Jupiter, so what you see here, the gray plane, is then what I call this solar system plane. So that's like the base is the plane where you have all the planets. And then you see the sun in the middle, and you see Earth, and you see Mars's orbit. And Mars's orbit actually is a little bit inclined compared to the solar system plane. And that's why you see it sort of going up and down into the plane. And you can see that Jupiter's orbit is also slightly inclined compared to the plane. And this is the Earth-Sun plane that it's compared to. Juno is the green trajectory. So Juno was sent up from Earth, and then first it did the little green cycle where it crosses Mars's orbit at what is called EFB. And then it flies further out than Mars's orbit, and then it flies back in towards Earth, where it crosses Mars's orbit again. And then it does what is called a gravitational lift. So it actually makes a flyby very close to Earth, where it actually sort of gets dragged by Earth's gravity towards Earth. But since Earth is moving around the sun, if you have done your calculations right, you make sure that the spacecraft moves towards Earth, but it actually just misses Earth because Earth has moved, so that it actually gets a swing by where it gets some extra velocity. It steals some of the rotational energy from Earth and gets some extra speed outwards. And also you can do your maneuver such that it actually gets a different trajectory so that you can get out of the plane. And since Juno was to look at the poles of Jupiter, the idea was to get it above the solar system plane. And that's why you see that the second trajectory from EFG of Juno actually sort of goes up and towards Jupiter in that way. So the important thing to notice here is that we cross the orbit of Mars twice with Juno on the way out and the way back in for the gravitational assist, and then above the plane of Mars. And that's important for the story. So that means that what John Leif realized that Juno was doing is that you imagine you have this butterfly net that collects dust, and it's actually collecting dust out to the other side of Mars's orbit, back in towards Earth, and then all the way out to Jupiter. And this is actually the first in situ measurements of dust in the solar system plane that has been carried out. It wasn't planned like that, but that's then what it ended up being. So here are the data where you have a plot that shows years, so time down on the x-axis. You can see 2013, 14, 15, 16. And then it shows the number of detections per day on the y-axis. And you can see that we actually had quite some detections. And then it's a little complicated because if you notice that there's an arrow at the top going inbound in ecliptic, so that's when we are going back to Earth. And then you have something called outbound of ecliptic, and that's when we're going on the second trajectory above the solar system plane. And the thing to notice is that we have a lot of measurements as we are going in when we're crossing Mars's orbit. And we have a lot of measurements again when we're going out towards Mars, which is at sort of the blue step. And then we have basically nothing from the asteroid belt out to Jupiter, except that we have 2 comets. So we're passing through 2 known comets. And that's actually why we think that this, as crazy as it might sound, this idea, it's relatively sound, because else we wouldn't have detected the trails of the comets, and the trails of the comets are exactly where they're supposed to be. And the fact that Juno picks it up, and it picks it up at the count of day that it does, actually makes us feel relatively confident about our interpretation. So this is another plot trying to show what it is we think. So we see, so you have again the plane of the solar system. It shows the orbit of Earth, it shows the orbit of Mars, and then the green shows how Juno came in towards the orbit of Earth and then moved back out, so that we both have sort of the plane and then we have above the plane. And we measure dust in both situations, but different amount of dust, which can tell us something about how the dust is distributed in the solar system plane, so how the zodiacal light is distributed. Because you have to remember, when you observe zodiacal light from Earth, I mean, we just see that you have dust in this plane. We don't know where it's coming from. We don't know, how it's positioned in the line of sight. But actually here we actually have an in situ measurement of how it's positioned in the plane between Earth and Jupiter in the trajectory that Juno followed. And what was astonishing to us was that as Juno was passing through the asteroid belt, where if you had asked me before, where would Juno expect to measure most dust, I would say it has to be in the asteroid belt, because all models indicate that the dust that we get in the zodiacal light comes from the asteroid belt. You have these asteroids that occasionally collide, and we can see asteroids which has chipped up chunks like Vesta. So we are absolutely certain that asteroids collide, they produce meteorites. Meteorites have landed on Earth. We know where the origin of the meteorites are, so there's no doubt that asteroids get chipped off. And in that process, of course, you also produce dust. So the general conception was that this is your source of dust, is the colliding asteroids. But that actually was the most dust-free area that Juno flew through. That was actually in the asteroid belt. And then that really puzzled us. But once you start thinking about it, it actually makes sense, because in the asteroid belt, you have relatively many asteroids. So even though they produce dust, you also have a lot of asteroids sort of coming by relatively quickly and sweeping up the dust, because, as they move through, they will just sweep the area that they move through clean. So the fact that you have no dust in the asteroid belt, even though it probably produces dust, actually makes a lot of sense. So around Mars, we found a lot of dust. So we thought, okay, maybe it's actually Mars that leaves a dust trail. And as you know, you have little dust storms on Mars. So we were thinking maybe it's not impossible that some of this dust can be levitated in the atmosphere, and then it actually leaves a trail of dust, and this dust is then spread out, and it actually explains what we observed, and it fitted very nicely. The only problem is if you actually sit down and you start calculating the escape velocity of a little dust grain from the surface of Mars, and you look at the Martian atmosphere and what we know about it, then you run into trouble because you need sort of basically supersonic dust. So I mean, it's not obvious that it's actually possible at all. However, there has been observation. So here's a paper by Chance La Vega et al. From 2015 that was published in Nature, where they actually observed high up in the atmosphere plumes of dust. So that you have these dust storms of Mars, and occasionally you apparently can have weather situations where you have these plumes of dust, which actually does seem to levitate dust that goes into to outer space, that actually manages to reach the escape velocity of the dust grains. And just to show you a plot where it's maybe more obvious. So here on the x-axis you have the altitude, so the height, and you can see the solid red line that you actually get up to approximately 280 kilometers about the Martian surface. And Mars has about 1/3 the gravitational pull of Earth, and the International Space Station is at a height of 400 kilometers above Earth. So that's actually quite high up about Mars, and actually the gravitational pull is not very large at such a high extent. So we think we can't prove that you can get the dust, and we can't explain it in detail, but we think it's not unlikely. And the Juno data actually fits very, very nicely if most of the zodiacal light actually has an origin of Mars that works very neatly. So that's what our paper is about, is that we think, okay, the zodiacal light, the origin is probably not, the main source is not the asteroid belt. The asteroid belt can contribute just like comets can contribute, but the main source we propose is Mars. This has, of course, given us quite some opposition. So we have encountered many referees who were, actually our referees fell in two categories. Either they were super excited and thought it was a great idea and they really loved the data, or else they just hated our guts and thought that we should just study the literature because everybody knew that it was the asteroid belt. And even Brian May has written his PhD thesis on it. And Brian May's supervisor basically think that we are complete morons and idiots. And of course he might be right. But I'm hoping that this can trigger some new blood into the Zodiacal Light Society, so that maybe they get so eager to disprove that we are wrong, that they might actually be able to prove that where does it actually come from if it's not Mars. But I must say, I'm a strong believer in data and the Juno mission. I mean, you have data, and of course the way that we interpret it, because we don't, that's really the weakness. We don't see the dust directly. We see the larger dust grains that we estimate are between 8 and 80 microns. So they're quite big gravel little pieces, because they need to be that big in order to actually chip off pieces of the solar panels. So that's the idea of the paper. One thing I love about astronomy is this aesthetics and the beauty. And since we are talking about the Juno mission, and even though I'm not part of the Juno mission, I managed to sort of sneak onto this paper because I knew something about dust and they didn't. Then I just want to show you some of the fantastic images from Juno. So this is the upper atmosphere of Jupiter. And the reason that it looks a little different than we normally see it is because the Juno is observing in the near infrared. So it's not just the optical. So we can actually see the upgoing and downgoing streams of the atmospheric stripes that you have of Jupiter, and tornadoes that you have on Jupiter, and it's really amazing. And here you have the large moon Io, putting a shadow on Jupiter. So this is just the shadow of Io as observed by Juno down on the surface of Jupiter's cloud layer. And here you have the great red spot and that belt stream. And here you have a close-up of the great red spot, which is a high-pressure tornado which has been observed for at least 400 years. So we don't know how long it's been there, but at least humans have seen it for 400 years. It's much smaller now, apparently, than it was some 100 years ago. So it seems to be diminishing in size. But I think it's amazing to see so much structure between the east and west going belts and the up and down going belts on Jupiter. So with that, I would like to say thank you for your attention. I hope I have sparked some interest in the Juno mission, and also given you an idea that sometimes you design an experiment and it turns out it gives you a different result that you even expected, as Juno has. And also, I mean, look at the webpage of the Juno gallery. It's amazing pictures. And with that, I'll be happy to take any questions that you might have.
Thank you, Anya. I hope everyone enjoyed learning about zodiacal dust. Those images from Jupiter and Juno were pretty amazing. So I guess maybe I'll go into the gallery view. Oh, probably not. Sorry. Streaming stuff I'm still bringing out. But we already have some questions, which is pretty great. So if anyone has questions, please write them in the chat. So Jürgen asked, there must be a correlation between the impact force of the dust particles and the amount of photographed debris detected by the camera.
Yeah.
The camera can only detect a fraction of the dust. So I guess... do you want to elaborate on that?
So that's somehow the weakness of our paper, because we make some assumptions, right? We think, okay, and here, I mean, every time you have something in space hitting, right, you have impulse, you have the sort of velocity and mass, right, is somehow connected, right? So you assume either a certain mass or you assume a certain velocity, and somehow they're both important. So what we can see in the way that it hits and the debris flies, that we think we have a good handle on the incoming trajectory of the particles. And some of them we have actually been able to get a few observations where you can actually see something coming in. So we have been able to have a few of the data points where we have some handle, and based on that we sort of made a model saying, okay, when we see this kind of impact, then it's due to this size of dust grain. And then we actually in the lab, we have, thrown gravel at the solar panels, mimicked to find out how much would it actually take to actually chip off pieces of the solar panel. But there is a lot of assumptions going into that. So I think that is a fair weakness. So I'm not certain that we are right at all. And I'll be happy enough to be disproven, because I think it's the way we sort of interpret the data. And we discussed a lot whether we should actually hang on to the paper longer and try to be more certain about what we did. But we thought it would be more real to actually put it out there and then have people criticize our guts, but actually also help finding out, because there are people who know a lot more about zodiacal light than we do. And if they get annoyed enough, then maybe they will actually take the data, look at it, compare it to other data, and come up with a better explanation. And that's what science is about. So I'll be happy enough about that. I mean, I like the little idea of, dusty little Mars moving through space. But I mean, that's just because it gives such a nice image. I mean, it doesn't have to be correct, right? I mean, I also like comets, and asteroids are fine, right? So all is good. We just want to find out what it actually is.
Yeah, it's a interesting strategy to try to annoy other research teams to doing more research. Okay, so we have another question, which is, are there plans for a new mission that can elaborate more on this research?
I mean, there's always plans for putting things further out, right? So we're hoping also by putting this paper out we can convince other missions that's going beyond Mars to actually have like star trackers or something else where they will or a dedicated measurement to actually something which can measure the dust in situ and not like by proxy as we do, but will actually measure the situ, because there has been missions up like the Ulysses mission, which has actually measured dust particles, but they have mainly measured very tiny dust particles because that's what they expected. So that's what they have been looking for. So the fact that we see large dust particles, they cannot be certain is not there just because they didn't see them, because their instrument was not designed for that, right? So maybe the next instrument that's going to fly further out will be turned on all the way, and it will actually be built such that it can do a broader range of grain sizes, now that we seem to indicate that maybe some of the dust is larger pieces than they were expecting to collect, so that we'll get the answer in the future.
Yeah.
I mean, once you're flying something, having a little dust measurement, I think it's not that much more expensive, but it's probably very expensive.
Yeah.
It's always
Sending
expensive.
things to space is
Sending
hard.
things to space, right? But I mean, Elon Musk is sending 12,000 satellites to ruin the night sky. So, maybe they can build a little rocket that can collect dust,
The light, that would be handy. Okay, I guess this is a comment. So Jupiter, good comment. Jupiter is like a miniature solar system altogether in itself. Juno is an exciting mission indeed. Thank you for this very informative talk. So thank you, Roger. We have a question from Nikki, which is, what could be the origin of the dust particles on Mars? So you mentioned the dust storms. Is that the main one?
Yeah, so the reason that you have a lot of dust on Mars is actually because you have the atmosphere, and the atmosphere, so the wind just grinds down the stones, right? So just like you have on Earth, that mountains just get grinded down by the atmosphere. On Earth, it's more effective because the atmosphere is thicker, so it can move more mass, more sand. On Mars, it's a slower process, but Martian dust is very, very fine grained. I mean, as we've seen by Perseverance, who just landed, and Opportunity, who's there, and Spirit, and Curiosity, who's also still driving. So actually, there is a lot of very, very fine grained dust on Mars. But remember, we cannot really explain how to levitate it. I mean, because one thing. So we've seen the plumes, and it seems like, I mean, that's an observation, right? And I am an astronomer, and I believe strongly in observations. Theory is great, and there's all these theoretical physicists doing astronomy beyond, or theory beyond physics, basically on early something. But I do believe that if you do an experiment and it shows something, that somehow, unless you can explain that the experiment was wrong, that is much stronger evidence that you need to deal with these that you actually see dust up high. And then, even though if we cannot explain it yet, then maybe the next Mars mission need to look more into that, right? Because it's probably some super interesting weather phenomena, would be my guess.
Yeah. We have another question from Bo. So, fascinating story. What would be the best way to further prove or disprove this theory? Would it be observations with telescopes from Earth or measurements from space probes?
I think measurements from space probes, but I will not exclude that one could actually do some observations from Earth, because, I mean, telescopes have improved a lot. Astronomers are super smart at getting lots of information out of really crappy data. So I wouldn't disclose that there couldn't be a really smart PhD student or postdoc out there who would be able to somehow come up with an idea where you could distinguish, saying, okay, if it is Mars, then it would do this, and if it's asteroids, it's going to be more homogeneous because the asteroid belt is more homogeneous while Mars moves around, and it's going to be most dusty behind Mars and not where in front of Mars before, it sort of picks up the dust. So I will not exclude that you could do something very smart. I mean, that's one of the good things about being an astronomer, is that there's so many much brighter astronomers out there that you can talk to and work with. I mean,
Okay, so if people have more questions, you can type them in the chat. I have some questions myself. So I guess maybe you wouldn't know this, but maybe you do. So when the engineers discovered the dust particles were whacking into the solar panels, would that significantly degrade like the lifetime of the solar panels, or is it still so little that Juno will still be able to do its whole mission?
I mean, Juno has already done its full mission and is on extended lifetime, so it wasn't super damaging. Actually, it turned out what was more risky for them was that once they came up to Jupiter, it turned out that even though Jupiter doesn't have rings like Saturn, but it has a lot of leftover rings, and it turned out that there was some seriously larger boulders
in the rings
around Jupiter that occasionally came surprisingly close to the spaceship. So right when they arrived, they realized where not to be. That there was some zone of avoidance that they were not aware of until they got there. So it just shows you every time you send up a space mission, you discover something new and exciting. No, so far, I mean, Juno is on an extended mission, so it's doing very well. It's quite exciting, and the paper that we're publishing is part of a special edition on Juno. So it's a collection of all the exciting Juno results. So that's it's a big thing with lots of great papers.
Yeah. We have a couple more questions and we might wrap it up after that. So one question from Danielle Melisani.
Melisani,
there you go. Can you tell / do you recall roughly how wide the dust zone around Mars is? So I guess would it extend beyond the asteroid belt or out to the asteroid belt, or?
Yeah, so actually, there is something called the what is it called? The
Kozai-Lidov?
Exactly, the Kozai-Lidov effect. And if you take that into account, you can explain that you both get some dust that moves further out than Mars's orbit and some dust that moves further in than Mars's orbit. So at least if we've done the calculations correct, it actually, we feel that it shows why the dust belt has the broad feature it has around Mars, that it could originate from Mars and then be spread out to a larger area so that it fits the data.
Okay, yeah, because it is surprising to think that Mars is so small, but its dust can contaminate such a large area.
Yeah, but I guess it's like a car with its exhaustion, right? It doesn't just come out like a water hose, right?
That's true, yes.
The solar wind to, doing all kind of fun.
To blow it around. We might take the last question from Louise Hopner. Do you ever get tired of dealing with astronomy in space? I gave up on it because everything is so far away and hard to measure. That's a good question.
Yeah. No, I had some years ago, I had sort of a semi sort of thinking, oh my God, I worked all my life on dust and we still don't know what the origin of dust is or where it comes from, and all the ideas we've had now turned out to be wrong, and now we're sort of back at zero and I can spend my whole life on it, and we probably will know just as little when I die as, when I entered the field, and I felt, what's the point, right? And then we had some new observations and some new ideas, and so no, I don't really get tired of it. I think my main problem is actually that I always feel I have too little time to do it because I'm doing public outreach. And there's one thing I would like to say, that next year in 2022 is going to be the United Nations. So UNESCO has decided it's going to be International Year of Basic Science and Development. Mm-hmm. And in Denmark, to play into that international year, so me and a few others are organizing Videnskabsår 2022, so the science year 2022. So there's going to be a lot of exciting science going on that year, and a lot of focus on science. And it starts 1st of December this year. det videnskabsår and ends on the 10th of December in 22 when the Nobel Prize is handing out, because we're celebrating Niels Bohr's Nobel Prize in Physics, which was the first Nobel Prize in Physics that Denmark received. So there's going to be a lot of fun going on.
That's really neat. We'll be sure to share some of that, those details of
and
as well.
And the whole web universe we're building up, remember to remind me of Astronomy on Tap, because then we can, spread it out as well.
That'll be good. Okay, well, we'll thank Anya again. Thank you so much. This was a wonderful talk, and we had lots of great questions. So yes.
Thank you for
That's okay. I think we'll pass on to Nikki. So Nikki, did you want to take over?
Yes. Okay, so about the quiz. We got 12 responses, so thanks for that. And before I will announce the winner, I'll just shortly go through all the questions and give the solutions. So the first one was, are solar neutrinos harmful? And the answer was no. The second one, how many neutrinos are emitted in a supernova explosion? Which was 10 to the power 58. How many types of neutrinos do we know to exist in nature? Which are 3 types. And then how long does it take a supernova to make gold? Which is only a few seconds, which for astronomy especially is very short. 5, what is more correct to say about the mass of a neutrino? The right answer is it is less massive than an electron. And then going to the questions about women in astronomy. So which of these discoveries have been altered or co-altered by women? And actually all the solutions were correct. So radio pulsars, indirect evidence of dark matter, supermassive black hole at the center of the Milky Way, and luminosity period relation in Cepheid variable stars. And then based on a 2018 survey of representation of women in science and engineering in the European Union, where does Denmark rank? Where the first place means it has the highest fraction of women in these areas. And this was in the top 5. And then a question about Cecilia Payne-Gaborschken, who grew up in England, but then moved to the US to study. And why was that? Which was sadly because most universities in the UK did not award degrees to women. And then the Nancy Grace Roman was, she was an astronomer and a NASA manager who played a pivotal role in the realization of the Hubble Space Telescope. And actually, they are building a new space telescope now, which is named after her. How many women have been in space compared to 566 men? 65 women. And then the tiebreaker question, 216 Nobel Prizes in physics have been awarded. So how many of those were awarded to women? We had answers ranging from none to 50, and the correct answer was 4. So only 4. So well done. So I'm just going to name the top 3 for the quiz. So on the 3rd place with 11 points out of 13 questions, we have Jürgen Skut. So well done. For the 2nd place with 12 points out of 13, we have Ocho Nero. Not sure if I'm pronouncing that correctly. And then for the final, the first prize with full points, 13 out of 13, we have DTU team. So congratulations. And yeah, please contact Astronomy on Tap on Facebook, and then we will make sure that you get tickets for the next real life event. And yeah, we hope you all enjoyed the quiz, and we'll be back next time. Yeah, and then I'll give it back to Reggie again.
Yeah. So let me go to the gallery. So yes, hope you enjoyed the quiz. So contact us on Facebook or email us, and we'll give you some free seats at our next live event and drinks. But I think that concludes our March event. We hope that you enjoyed hearing these great talks from Professor Irene Tamborra and Professor Anya Anderson. And our next event is April, and the theme is Extraordinary Earth. So we hope to see you there.